Welcome back, everyone. Canada is stepping into a new era of high-tech surveillance with the introduction of advanced drones equipped with quantum sensors across its vast Arctic region. These are not ordinary drones. The onboard quantum systems can detect even the smallest disturbances in magnetic or gravitational fields, allowing them to identify hidden submarines, aircraft, or even troop movements beneath ice or snow. In a place where traditional radar struggles and weather conditions make satellite imagery unreliable, quantum sensing may provide Canada with unmatched visibility and control. This effort marks a shift in national security strategy, blending innovation and environmental resilience. Quantum sensors operate by detecting changes at the smallest possible scale using the principles of quantum mechanics. These sensors often rely on particles such as atoms or photons to measure changes in environmental fields like gravity, magnetism, or acceleration. In the harsh Arctic regions of Canada, traditional sensors can be disrupted by ice, snow, and geomagnetic fluctuations. Quantum sensors, however, are immune to many of these issues because they measure quantum states that are incredibly sensitive to small changes. This sensitivity gives them a distinct advantage in detecting movements or objects that would otherwise be invisible to radar or satellite imaging. In practice, quantum sensors might use atomic interferometry to measure gravitational anomalies. This means they monitor how clouds of ultra-cold atoms fall or move in response to local gravity. A submarine, moving under Arctic waters, for example, slightly alters the gravitational field in its vicinity. Quantum sensors aboard surveillance drones can detect these tiny changes and infer the presence of the submarine, even if it is well below the ice sheet. This allows Canada to detect threats or foreign incursions that are currently difficult or impossible to track using sonar, satellite, or radar-based systems. Another application involves magnetometers that use quantum effects to detect small changes in magnetic fields. These devices are able to register minute fluctuations in the Earth's magnetic field that occur when a metallic object, such as a stealth aircraft or a buried facility, passes nearby. Arctic regions experience unique magnetic conditions that can disrupt conventional magnetic sensors. But quantum magnetometers are immune to much of this interference. They are also compact and require little energy, which makes them ideal for long-range drones that need to operate independently for extended periods in remote environments. Quantum sensors are promising for inertial navigation systems. When GPS signals are blocked in polar regions, drones need a way to track their position. Quantum accelerometers measure drone movement with extreme precision without satellite signals. These accelerometers observe interference patterns in quantum wave functions as the device moves. This allows the drone to maintain an accurate record of its position, speed, and orientation, which is critical for navigation and targeting in Arctic zones. Temperature and vibration noise are major problems for traditional sensors in polar environments. Quantum sensors often operate using cooled atoms or superconducting materials, which means they are already designed to work under extreme conditions. Canada's Arctic drones can exploit this advantage by integrating these sensors into shielded modules that remain stable regardless of external temperature swings. This level of environmental tolerance means the drones can remain airborne longer, require fewer maintenance intervals, and operate with a level of precision that just wouldn't be possible using older technologies in such an unforgiving climate. Communication and data security are also influenced by quantum technology. Some quantum sensors can be used alongside quantum key distribution systems, which allow drones to transmit surveillance data back to Canadian command centers with virtually unbreakable encryption. The same quantum principles that make the sensors sensitive to environmental shifts also make any attempt at intercepting communications detectable. If someone tries to eavesdrop or interfere with the transmitted data, the quantum system alters its state, revealing the intrusion. This creates a dual layer of defense where both observation and data flow are hardened against outside threats. The real-time processing of quantum sensor data is another field under active development. Because quantum systems gather information on such a fine scale, the data volume is enormous. Canada's drones will require onboard processors that use machine learning to filter and interpret this information rapidly. Rather than sending raw data back to base, the drones can process and evaluate it in the sky, recognizing patterns that indicate the presence of a foreign vessel or unexpected environmental change. This makes the system responsive and autonomous, enabling quicker decisions in high-stakes scenarios. Deployment across the Arctic will likely occur in phases. Initial drones may operate in test zones where specific threats or environmental targets are being tracked. As the technology matures, Fleets of drones could be assigned to patrol different sectors, each with its own mission profile based on quantum sensing. Some may monitor undersea movement, while others track aerial activity or magnetic anomalies around known geopolitical flashpoints. With enough drones in the air, Canada could create a continuous surveillance net capable of detecting even the smallest incursion within moments of occurrence, offering unparalleled domain awareness. There are also plans to integrate quantum sensors with other advanced drone systems, such as optical recognition, radar, and synthetic aperture imaging. While quantum sensors provide unmatched detection of physical field changes, these additional layers give context. If a quantum sensor detects a gravitational anomaly, for instance, an onboard camera or radar can immediately lock on and gather visual or spectral confirmation. This layered sensing approach transforms the drone from a passive monitor into an intelligent system capable of autonomous tracking, confirmation, and classification of potential threats in real time. One promising application is environmental monitoring across Canada's vast and rapidly changing Arctic territory. Quantum sensors can detect shifts in permafrost, ice sheet movement, and underground water flow by measuring subtle gravitational or magnetic changes over time. These drones could fly repeated routes and compile detailed maps showing changes in the Arctic landscape due to natural processes or human activity. This data would be invaluable for researchers studying climate dynamics, animal migration patterns, and long-term geological shifts. It could also assist in forecasting avalanches, ice collapses, or other natural hazards that threaten communities and infrastructure in the far north. Another potential use case lies in resource exploration and territorial security. Quantum sensors mounted on drones could scan remote Arctic regions for mineral deposits, petroleum reservoirs, or other subterranean structures by detecting density variations in the Earth's crust. Unlike ground surveys, this airborne method allows for broad coverage with minimal disruption to fragile ecosystems. In contested zones, the same technology could detect unauthorized drilling or construction activity below the surface. This dual capability supports both economic development and sovereignty enforcement without needing large numbers of personnel on the ground in harsh or politically sensitive areas. A final possible application is in disaster response and search operations. In the event of a downed aircraft, trapped vessel, or natural disaster in remote Arctic zones, quantum-equipped drones could scan the area for human signatures by detecting unusual magnetic patterns or minor gravitational shifts. This would be especially useful in snow-covered or fog-obscured environments where visibility is limited. Combined with infrared imaging and autonomous flight, these drones could locate survivors, guide rescue teams, and assess structural integrity of nearby terrain or facilities. Such capability would dramatically increase the safety and speed of Arctic emergency responses. As Canada deploys more of these quantum-enabled drones, the implications reach far beyond national borders. Other Arctic nations are watching closely, and this could trigger a new technological race in northern defense systems. But the same tools may also help with climate tracking, wildlife monitoring, and mapping shifting ice formations in real time. The fusion of quantum science and autonomous flight is still evolving, and Canada's Arctic strategy might soon become a model for other nations. Thank you very much for watching. Please like and subscribe.